Hey, so this talk is going to be on reviewing probability and getting into conditional probability and a little bit more sophisticated techniques in calculating probabilities. So first, a little bit of a review. Remember the sample spaces. An experiment is an occurrence with a result or an outcome, and the set of all possible outcomes then is called a sample space. So an example of this is that, let's say you have an experiment in flipping a coin. You have two possible outcomes, heads or tails. And so the sample space that we have is the set heads or tails. So all the things that we've talked about regarding sets and intersections and unions and things of that sort will come into play in counting up sample spaces and different sets of occurrences or outcomes. So for example, if we have an experiment that we're going to flip a coin and roll a die, the outcomes are possibilities of the coin having a heads or a tails and the die having the numbers 1 through 6. And so we would call the sample space the set of those things, the set of H1, H2, H3, and so on, and all the way to tails and a 6. So given a sample space, we call an event some subset of S. So if the outcomes are called they're called favorable if they're one of the elements of the event E that we're looking for. So to give an example there, if you have an experiment of rolling a die and your event is that you would have an even number, the even number, or excuse me, not the even number, the number is odd, the set of outcomes possible is 1, 3, or 5, and so you would consider the outcome of 3 a favorable outcome. So the event is the whole set of what you're looking for, and the outcome then is the specific outcome that you get by conducting an experiment. So it just gives us the language of having a sample space, an event, and the outcome. The event, remember, isn't just the one particular outcome of an experiment. The event is the thing that we're looking for as a set. So if we're looking for odd numbers, we call the event, in this case E, the set of 1, 3, and 5. And so we may have an outcome that may be an even or an odd number, but if it's an odd number, then we consider that a favorable outcome. In other words, it's a member of the event that we're looking for. Okay, so with probability, when we do one trial, how likely is it that this outcome will be in a particular event? So there's a couple ways to look at this. If we conduct an experiment, let's say that we do this a number of times to see if we can come up with a probability, we would count up the number of repetitions we would have, and then we would look at the frequency of the event that we're looking for. So in other words, if I'm rolling a die and I do it 10 times, the number of repetitions would be 10, and the number of times that when I rolled the die I would get an odd number would be that frequency of event E. So look at it as the relative frequency. So that's the amount that the number of times that it comes out relative to the number of times that you try. So this is an experimentally determined probability. Now this is very much related to the probability if we look at the underlying mechanisms here. And so our textbook doesn't make any distinction between the notation. It's always P at E. And here I'm just making it just so we can distinguish between what we're looking at in terms of one that's derived from the mechanisms of what's going on versus the observation of what we see going on. And so if we do it from the mechanism standpoint, we can count up the number of favorable outcomes to the number of total outcomes. So in other words, the favorable outcomes would be 1, 3, and 5, and the total number of outcomes would be 1, 2, 3, 4, 5, 6. So the probability established that way is very definite. It's going to be 1/2. The probability of us doing it experimentally by looking at the frequency of a repetitive trial, that may not get us exactly the right probability. We would have to do it a very, very large number of times, and we would expect the probabilities then to equal each other only if we try enough experiments in the long run to get to the event that we're looking for. Okay, so then in set notations, remember we talked about cardinality, and we'll be dealing with cardinality of sets. So the cardinality of the event that we're looking for, and the sample space, the ratio of that is the probability. Okay, so here's a question you might want to think about. So an ordinary deck of playing cards has 4 suits, and each suit has a 2, 3, 4, 5, 6, 7, 8, 9, 10, a jack, queen, king, and an ace. So that's a total of 13 cards. So what is the probability of drawing a heart? And what is the probability of drawing a 4? So the event in question number 1 would be drawing a heart, and you have 13 hearts, as you do for every suit, but we have a total of 52 cards. So that probability then would be the number of hearts divided by the number of playing cards, and so that would be 13 over 52, or reduced, it'd be 1/4. So we would expect in the long run that if we're drawing a single card out of a deck of cards, that about 1/4 of the time we would get a heart. So the probability of drawing a 4 is similar, except that we have the number of 4s in a deck is just 4, and we have 52 cards in a deck, so that would be 4 divided by 52, or 1/13. So let's move on to probability of unions, intersections, and complements. Now, we already know that the set E and its complement E would make up the universal set. So if we take if we know what the probability of E is, we'll know what the probability of the complement of E, because the two probabilities have to add up to 1. And so this is useful in a little different form. Like if we're looking at the probability of something not happening, we can calculate the probability of it happening and then subtract that from 1. So very often when we're doing probabilities, it might be easier to look at the probability of something not happening, and then when you subtract that from 1, you get the probability of it happening. So what about unions? Okay, so remember we have unions and intersections in sets. And so what we're going to deal with here is just an example. Let's say our sample space is what a die is, 1, 2, 3, 4, 5, 6. And so we're going to look at, getting a little ahead of myself here, we're going to look at the probabilities of A and B happening. So A means that you're going to get a small number when you roll the die. B means you're going to get an even number. So the probability of getting a small number, you have three small numbers divided by 6, that's 1/2. The probability of getting an even number is the same probability, but it's a different set. So the excuse me. So the probability is you have 3 even numbers divided by the total number of faces you have on a die, and that's 1/2. So what about the union of A and B? And what does that mean in terms of probability? So the union of A and B is, remember, that's an or, either or. And so the probability that we're looking for is, what's the probability that we get a small number or we get an even number? And so remember the formula that we had for cardinality, where we can find the number in the union, in the set of the number in the set of the union And so that would be the number in A plus the number in B minus the number in A intersect B. So then when we do the calculation there, we know that there's 3 elements in A, there's 3 elements in set B. The intersection of the two, we know that the 2 exists in both A and B, and so we can get the union of A and B as 5. And so the probability then of getting A union B, or a small number and an even number, is just that formula divided by the sample space, which is 5/6. So if we look at the complement of that, what if it's not in either set? We know that that's going to be 1/6. That would turn out to be just the number 5. The number 5 is not in either of the sets, and so 1 out of 6 times would be the complement of A union B. Okay, so if we see this from a Venn diagram standpoint, you can see that I've populated A and B with the members of the set, and you see that you have 1, 3, and 2 in A, and then 2, 4, and 6 in B, and the 2 is in both sets. And then the 5, which is in the lower left-hand corner here, is in neither of them, and so the probability of A union B equals 1 minus the probability of what's not the union, which is 5, so that's 1/6, and so we get 5/6. So any number of ways to count this up. Okay, so now let's look at conditional probability. Conditional probability is finding a probability when events do or don't depend on each other. Okay, so let's say, as an example, a farmer's market sells fruit and other things to children and adults. What is the probability that a child bought fruit? Okay, so let's make up a table that shows some data here. Oh, and before we show up the table, the way we're going to notate this is the probability of F, so buying fruit, given that it's a child. Okay, so if we have people who bought fruit and didn't buy fruit, adults and children, let's say we have these numbers just made up to show what we have in this particular illustration. So we would read this, of course, that we would have 500 adults bought fruit, 1,300 adults didn't buy fruit, so there was a total of 1,800 adult customers. A child, for children, 540 bought fruit, 400 did not, and so you had a total of 940 children. So when you add 1,800 plus 940, there was a total of 2,740 customers. So if you look at how many bought fruit, so the total between adults and children is 1,040, and the number who didn't buy fruit would be 1,300 plus 400 is 1,700, and you can see that these two numbers then add up to the same 27,400. Okay, so we can use a table like this to determine conditional probability. So let's look at a few probabilities first. If we look at the probability, if we're just looking at of the purchasers, what's the probability that if we chose one at random it'd be a child? So, well, there was 940 children divided by the total set of purchasers was 270, so the probability of a randomly selected person here would be 940 over 2740. The probability that they bought fruit, we can see that there's 1,040 bought fruit over the total population of 2740. And so when we look at intersections and unions, we see that, we can see that the intersection is how many were children that bought fruit. You can see that there were children that bought fruit, that's 540 divided by 2740. So if you looked at just that subset of the population of children who bought fruit divided by the whole population, you'd have the probability of the intersection. Now, the probability of the union, this would be the probability of children, of selecting somebody who was either a child or who bought fruit. We would take 940 plus 1040, and we would subtract 540 because that's the overlap, and we would divide that by 2740. So this is making use of that formula that gives us C union F. So we would take the probability of C, which is 940 over our denominator, the probability of F, which is 1040 over our denominator, minus the intersection, which happens to be this 540. And so we can calculate those numbers up to get those probabilities. Okay, so let's illustrate this with a Venn diagram and go back to our original question. What's the probability that when we select somebody that they bought fruit, given the fact that they were a child? Okay, so let's look at the Venn diagram that shows children is 940, adults is 1040. The intersection here is the number of people who bought fruit. And so we can make this probability, if you look at this from a kind of a subspace standpoint, where you have your population is all the children, which is 400 plus 540, and then divide that into what's in the intersection. So the from before, we had the probability of C intersect F as being 540 over 2740. The probability of being C, being a child, is 940 over 2740. But look, we have a common denominator in both the numerator ratio and the denominator ratio. So in fact, what we have is just 540 over 940. So hopefully you can see that if we define, let's say, a universal set that's just children, you can see that the probability of that child buying fruit would be 540 over the whole space there. Okay, so I'd like you to try, and this is just exactly just formulas here. So I'd like you to find what is the probability of A given that B has occurred. So if the probability of B is 0.5 and the probability of the intersection between A and B is 0.2, what would be the probability of A given B? And then we have a couple others to do here. If we have the probability of A given B is 0.2 and the probability of B is 0.4, find the intersection, find the probability of both of them happening. And then the third kind of common probability that we can find out, if we know the probability of A given B is 0.4 and the probability of A and B occurring is 0.3, find P at B. Okay, so push the pause and see if you can calculate these. It's merely applying the formula that we have at the top. And then think about what that really means, where if you have the probability of A given B. Okay, so hopefully you've all done these. So if we know that the probability of B is 0.5, and that's in the denominator, and the probability of A intersect B is 0.2, what we have is the overall probability is the probability of A given B is 2/5. The probability of A given B is 0.2. The probability of B is 0.4. Find the intersection. So the intersection, we know that A given B is 0.2. the probability of A intersect B is what we're looking for, and the probability of B is 0.4, so we know that 0.2 times 0.4 equals the probability of the intersection, which then is going to be 0.08. And the last one, if we have the probability of A given B is 4, the probability of the intersection is 0.3, we can find the probability of B as being 0.4 equals 0.3 over the probability of B, and so rearrange that, we get the probability of B equals 0.3 over 0.4, which is 3/4. Okay, so hopefully manipulating this formula isn't too challenging, but the real notion is to think about what it means to have the probability of A given B. And so okay, so then to recap what we've been talking about here, I'll give another example. Let's say we have people with blonde hair, brown eyes, blue eyes, and brown eyes, and I'll make up some numbers here. So this group of 180 people, you have 70 of them have blonde hair, 110 of them have brown hair, 80 of them have blue eyes, and 100 of them have brown eyes. So we can look at probabilities with these. We'll say the probability of blonde hair and the probability of blue eyes here. Okay, so I, rather than writing out the words blonde hair and brown eyes, what I'm doing is I'm making A stand for blonde hair, B standing for brown hair, C standing for blue eyes, and D standing for brown eyes. So the probability of blonde hair, which would be P at A, is 70, because we have 70 divided by 180. The probability for having blue eyes is 80 over 180, because we have 80 people with blue eyes out of 180. And so if we want to find the union of these two, where we say, okay, how many people, or what's the probability of choosing somebody from this group that has both, that has either blonde hair and brown eyes, that would be our familiar formula for unions and intersections, divided by the number of people in the sample space, so that's 180, and so we would have 70 plus 80 minus 150, or excuse me, 70 plus 80 minus 50 over 180. We have the probability of 100 over 180 is the probability of having either blonde hair or blue eyes. Now, let's say we wanted to do something with conditional probability. So we chose somebody, and we know that that person has blonde hair. What's the probability that they have blue eyes? And so we'll use our formula that says we take the probability of the intersection divided by the probability of the event A, which is the blonde hair, and we'll calculate those. But notice that it reduces down to 50 over 70, which is just the probability of blonde hair and blue eyes divided by the probability of everybody who has blonde hair. And so what we get is 5/7. And so we can really read these tables directly. It'd be easy, for instance, to find out what's the probability of somebody with assuming that, given that this person has brown hair, what's the probability of that person having brown eyes? Well, that would be 80 divided by 110, because you have 80 people who have brown eyes, a total of 110 people who have brown hair.